So in this video, I'm just going to give you a super brief introduction to um, tangent spaces and tangent vectors. In particular, I'm going to be, I would highly recommend Lee's introduction to smooth manifolds. You can legally find a free PDF copy online, but it's a book worth having. I think it's a great introduction that explains both some of the intuition and I'm going to be skipping a lot of the precise proofs in this particular discussion about tangent spaces. So I highly recommend consulting that. So what's going to happen is our main focus is to talk about tangent spaces. Okay, why? Well, so manifolds, right? We have this sort of abstract notion of shape, and you know, we want to be able to like do physics with it or something. So a common example we might give is, say, a map of temperatures, right? So imagine you have some sort of surface, and you're trying to study the thermodynamics of that surface. Well, you could have a function, right? So it's like this is our manifold M here. And we could imagine a function from M into the real numbers. And so generally we want this to be a smooth function, right? Something infinitely differentiable. And we could imagine at each point, what the value of the function is at that point is, say, the temperature of the surface at that point. And one thing we would want to analyze as well is, the study of how that temperature changes over the surface, right? I mean, physics is all about measuring rates of change, right? And so automatically you should be thinking, if you know some calculus, oh, rates of change, derivatives. So, okay, we should expect there's something going on with derivatives here. So how do we do this? Keeping in mind that, remember, we want to have our definition of manifold be independent of choices of coordinates, right? So you might think, again, if we're thinking about a manifold as embedded in Rn, which it is handy, but again, we want to try and avoid this coordinate dependent formulation, right? Then the tangent space is quite clear, right? Oh, you take a point and you can take some sort of like orthogonal plane there that just kisses the point, and you're like, okay, great, tangent space is well understood. But again, we want to try and formulate this in a coordinate independent way so that when we do put coordinates in, we can be sure that we're not picking up things that are just artifacts of that coordinate system. That is, we can translate between different coordinate descriptions. So how do we do this? Well, one thing to start is notice that even if we're thinking about this in Rn, right, I might draw these two separate tangent spaces. And if I were to do this literally in Rn, you'd notice that they would intersect somewhere, right? There would be some part where these planes cross, depending on how they're oriented. But we don't really care about this, right? Because if I'm thinking about the vector that starts at this point, which is describing the rate of change of some field over the sphere, I don't really care about what's happening at this other point. Like if those vectors happen to intersect, that doesn't really have a meaningful interpretation, because I'm sort of talking about rates of change at two different points. So psychologically, we want some way to distinguish between these tangent spaces. So one way of doing that is, so we're just going to talk about tangent spaces in Rn first, and then use the fact that we locally approximate manifolds by Rn. So in Rn, I'm going to define the tangent space at a point A in Rn to actually be all pairs A and V, where V is just some vector of a psychologically different copy of Rn. So now for each point at A, we have an entire vector space. So, addition and scalar multiplication sort of act in the quote unquote obvious way. So if I have AU and AV, I would define their addition to be AU plus V, and so on and so forth. And you can verify that this satisfies the definition of a tangent space. Okay. But now the thing is, so great. I have this definition of tangent vectors. But what I also want to know is that if I have some sort of field, right, if I have some sort of temperature gradients, I want to know how quickly it's changing and in what direction. So if you remember from multivariable calculus, we can do this with the directional derivative. So to be a bit more formal, suppose I have a smooth function, so some infinitely differentiable function on Rn. And at the point A, I want to know how that function is changing. So typically, I can just take the directional derivative. So this definition of our tangent space in Rn, then, I can use this to define an action of each one of these vectors. And that is just the directional derivative. So I'm going to define the action of a vector v sub A in the tangent space at A on F in such a way that it gives me the directional derivative. So we sometimes write this as d sub v, f evaluated at A, or the derivative of f, A plus tv, t equals 0. And something I want to point out, I mean, this isn't going to be too shocking necessarily at the moment, but it is important. It turns out that this, as you might expect, if you act on a pair of functions, it satisfies the product rule, right? So this is going to be VA multiplied by G evaluated at A plus F evaluated at A multiplied by VA acting on F. And it's a linear operator. This is going to be important in a moment for our generalization. In particular, if we imagine expanding this vector out in our standard basis, so here I'm employing, recall the Einstein summation convention of previous videos. Then if writing it out like this, the action of this vector on a function f is going to be just this sum, where it's these partial derivatives of these coordinates. So in fact, much more generally, it turns out that anything that satisfies this, we're going to call a derivation. So to be precise, and let me make this a definition for any manifold, because this is what we're going to use. So a derivation is a linear map that goes from the smooth functions on your manifold into the real numbers, and such that it just obeys this. So a derivation at P, I should say, such that it obeys the same law. So it'll be x f g at A plus f at A x g. And it turns out that in the particular case that we're focusing on first, in the case that m is simply Rn, it turns out that these coordinate functions are all derivations. Okay, not a big surprise. The derivative satisfies the Leibniz rule of derivatives. But it turns out that these actually form a basis for any possible derivation. Again, I'm making a lot of statements without proof in this video. Please consult Lee's Introduction to Smooth Manifolds. So in particular, this process of taking the ith derivative and evaluating at A, this forms a basis for the derivations. In fact, I'm now going to take this as the definition of the tangent space at an arbitrary manifold. This will help give us a coordinate independent definition, right? So we know that the derivations at a point in Rn can be identified with the tangent vectors at that point. And so in general, I'm going to define for an arbitrary manifold the tangent space at the point P to be all the collections of derivations at P. In just a moment, I'm going to give a more intuitive interpretation of the tangent space. And eventually, maybe I'll make a video about all the interpretations and doing it more formally, because it is really interesting. And I think one of the different views helps motivate the seemingly weird definition one sometimes sees in algebraic geometry. But in order to finish making this connection, something I should have done in the first video is define a map of smooth manifolds, because you should never be satisfied. I've said this a million times before. If someone just defines an object for you, you need to know what the morphisms are as well. That is an important part of what it actually means to define an object mathematically. Suppose I have a pair of manifolds, smooth manifolds in the sense we've been talking about. What should it mean to have a smooth map between them? Well, again, we have this local condition, right? So it should mean that, if we have some chart for this manifold, and we have some chart for this manifold, and again, we know what it means for U in Rn. So this should mean that for all points, we should be able to find some chart. So we have our manifold M, and we have this function. So here's M, we have, there's some sort of open set around it where phi sub alpha maps into Rn. Of course, if we have phi sub alpha inverse, that will go from Rn into here. And then our function, we have our other manifold, right? Our function f is then going to take this point here and map it to some point in our manifold N. And in turn, the manifold N, there's some V beta coming out of here, going into Rm. Perhaps I should have had those M's and N's swapped around, but that's fine. So ultimately, if we compose all of these things, we have a map from Rn to Rm, which we have a well-defined notion of smoothness. So we say that f is smooth if around every point in M, we can find a U alpha containing that point, V beta containing the image, such that this composition of maps, phi alpha inverse composed with F, composed with psi beta, defines a smooth map in the classical sense. Okay, and now we should expect that this tells us something about the tangent vectors, right? So we've talked about how these tangent vectors sort of tell us how a function on the manifold might be changing. So now we might be interested in how a function between manifolds, how that changes as we vary points in one manifold, how that affects the other. In other words, if I have this map of smooth manifolds, what I'm going to do is define a map between the tangent spaces of these manifolds. And well, what's something we can try? So I have some derivation, right? I'm taking this derivation definition of the tangent space. I have some derivation of P. I suppose I should call this capital F of P at N. And I have some function f, which is a smooth function on N. And so I want my function f, so we use this lower star, we call this thing push forward. I want this somehow to determine a derivation on in this tangent space, right? So I need to tell this to act on this function somehow. Well, what could I do with the datum I have here? Well, I know that already x itself is a derivation, so probably if I use that somehow, but the problem is that x is a derivation only on smooth functions of M. However, if f goes from n into the real numbers, little f goes from n into the real numbers, and big F goes from big M to big N, that means that the composition f and f this will determine a smooth map from M into the real numbers. So therefore, X can act on this composition. And again, I'll point you to Lee's introduction to smooth manifolds to see the proof that this is in fact a derivation, although it's relatively straightforward to carry out. Great. Okay, so this defines a map called the push forward of a smooth map, and we now have a map between tangent spaces. So let me now connect this to a more intuitive notion. So we think about, a manifold as having some shape. And, we imagine a tangent space, some sort of tangent plane here with all possible directional vectors. Now, one could think, imagine we want a tangent space just at some point. And if you just have sort of any path, any sort of just one parameter path going through that point, that has one particular, well-defined tangent vector, sort of being a sort of derivative at that point. And one could imagine by taking all paths through that point, you could end up with every possible tangent vector. And so with this sort of more intuitive geometric notion, we can make another definition of the tangent space. So if we take what we call a path through the point, so for us, that'll be a map from the open interval -1 to 1 into our manifold M, such that at 0, at time t equals 0, gamma is equal to p. Well, notice clearly the interval from -1 to 1, this is a smooth manifold. And so we can define the push forward of this map. And so another definition of the tangent space is basically the collection of push forwards of these maps. So rather, I should say of the image of the push forwards of the single derivation existing on this interval. And again, for the nth time, I'm going to suggest looking at Lee's introduction to smooth manifolds, which will really help connect this strange sort of definition of derivation to this more intuitive definition where we're thinking about derivatives of paths in our manifold. Okay, so that basically does it for today. That's just a quick whirlwind tour of what formally the tangent space of a manifold is. So we dress it up in this formal definition of derivations, but let's again, try to just bring it back and remember the thing that we're trying to capture is this notion of like having some sort of shape. There could be like an electric field or something, and we want to know, the strength of that field and the rate of change at each point. And so we can represent that with a vector, right? It gives us a magnitude and a direction. And the way that we've now defined this, again, is sort of in a coordinate independent way. So in the next video, I'm going to tell you about vector bundles. And this is going to allow us to sort of package up this information and now imagine an entire field on our manifold and express its rate of changes at every single point. So thanks again for watching, and I'll see you soon.